Welcome back to Module 2, the work. During this module, we're going to cover topics such as data and data selection and why we choose it the way we do. We're going to cover what an algorithm is and how algorithms are used in trading. And then finally, we're going to get into the real meat of things and define different statistical models and some background information about that. So data, we have two data vendors right now. One is DTNIQ feed and the other one is EOD data. And there are steps to selecting data from either one of these vendors. Step one is to have a market or markets in mind. That's your general market selection. Step two is to look at market depth, meaning how much volume does the market have at any given time when you expect to be trading. Step three concerns market volatility. You want to pick a market that has enough price movement for your strategy to be profitable. There are some markets out there that really don't move a whole lot, and you need to be aware of that. Step four regards the resolution of the price bars, or how much time each price bar represents. You want to select the appropriate time period based upon your research. And finally, step five is to be aware of the market hours. Every market is different when it comes to when the market is open and certain shutdown times, so you must be aware of that. Next, what is an algorithm? Well, algorithms are used in computer science and mathematics, and really all they are is a step-by-step procedure or set of rules that are followed. They can be used in calculations or just simple logic that you want followed. We'll get into an example of an algorithm next, but how is it used in algorithmic trading? Well, really all it is a trading system. In this case, we'll use some mathematical models for making transaction decisions in different financial markets. You build rules into the model and determine the best time for an order to be placed. And then you want to cause the least amount of impact on the security's price. And there are also algorithms out there that when you're dealing with big banks, they have such large amounts of capital. Having algorithms break up the amount of contracts to each market maker, so that way you're not buying one lump sum, because that'll affect the market too much. If you go out in several different market makers and buy small lots at a time, that won't nearly affect the market as it would if you did it in one lump sum. So to begin with developing an algorithm, you write pseudocode, which is shown here. It can be either written out like it is on the left-hand side, or it can be in a flowchart form, as you can see on the other. Either way is okay. If you have a more complex algorithm, it's probably easier to write it out. Flowcharts tend to get messy and confusing. An example of an algorithm we'll go through on the next slide is with Sheldon from the Big Bang Theory, having a discussion with Kripke on the phone, talking about their friendship and what they can do together to rekindle their friendship. It gave me a laugh, and hopefully you enjoy it too. So let's watch that.
Just in time. I believe I've isolated the algorithm for making friends.
Sheldon, there is no algorithm for making friends.
Well, hear him out. If he's really onto something, we could open a booth at Comic-Con, make a fortune. See, my initial approach to Kripke had the same deficiencies as those that plagued Stu the Cockatoo when he was new at the zoo. Stu the Cockatoo?
Yes, he's new at the zoo.
It's a terrific book. I've distilled its essence into a simple flowchart that will guide me through the process.
Have you thought about putting him in a crate while you're out of the apartment?
Hello, Kripke. Yeah, Sheldon Cooper here. It occurred to me that you hadn't returned any of my calls because I hadn't offered any concrete suggestions for pursuing our friendship. Perhaps the two of us might share a meal together. Yeah, I see. Well, then perhaps you'd have time for a hot beverage. Popular choices include tea, coffee, cocoa. I see. No, wait, don't hang up yet. But what about a recreational activity? I bet we share some common interests. You tell me an interest of yours. Really? On actual horses? Tell me another interest of yours. Oh, no, I'm sorry. I have no desire to get in the water till I absolutely have to. Tell me another interest of yours.
Uh-oh, he's stuck in an infinite loop.
I can fix it.
It's interesting, but isn't ventriloquism by definition a solo activity? Yeah. I mean, tell me another interest of yours. Is there any chance you like monkeys? Yeah, what is wrong with you? Everybody likes monkeys. Hang on, Kripke. A loop counter and an escape to the least objectionable activity. Howard, that's brilliant. I'm surprised you saw that.
Gee, why can't Sheldon make friends?
All right, Kripke, that last interest strikes me as the least objectionable, and I would like to propose that we do that together. Tomorrow. Yes, I'll pay. All right, goodbye. All right. Time to learn.
So that's a real life example in Sheldon's world of what a friendship algorithm looks like. Next, let's get into some math and how it can be useful in developing an algorithm. So we'll go through some background information of different types of models and statistics just to make sure we've covered all the bases and fully understand it. So first let's tackle the difference between univariate and multivariate. Univariate is simply the analysis and testing of only one variable against the dependent. Not much more complicated than that. As you can see, we have one x variable against the dependent. You know, there's no 3D shape there. That's all it is. Multivariate is the analysis and testing of multiple variables. You can see here we have two independent variables against one dependent variable. And you can see how the shape of the graph there changes. Next are simple descriptive statistics. These include size of the sample, measures of central tendency, box and whisker plots, variance and standard deviation. We'll go through and explain each one next. I want to start with, on this slide, what is sample size? You may already know, but it's simply how many observations you have in your analysis. It could be otherwise termed as n size. We'll see the n later on. So the measure of central tendency is simply measuring the middle using the mean, which is the average, the median, which is when you line up the values from smallest to largest, which one is in the middle, and the mode, which is the value that occurs most often. If the distribution is normal, the numbers should all be relatively close to each other. In the picture that we have below, the distribution is skewed. So as you can see, the mode, median, and mean are all different. So skewed distributions will pull the numbers apart. Next, box and whiskers plots. You may think they're simplistic, and they are, but they give a good general picture of what a distribution looks like. And they can be very valuable. So let's go through an example. We sample 2,850 people about how many hamburgers they've consumed during the past week. We line up their responses from smallest to largest, and we graph them, and we get this chart here. The top 50% are those who ate more hamburgers and are represented by everything above the median. So they ate more hamburgers than average, or the median. Those in the top 25% of hamburger eating are shown by the top whisker and the dots on, above that top whisker. The dots in this case represent outliers. Here we have 3 upper outliers and 1 lower outlier. This is a fairly normal distribution here. If it's skewed more to one side than the other, this will show it. And it's a very nice tool to have for a quick overview of the distribution, and it tells you how many outliers there are and the maximum and minimum without being an outlier, and it gives a lot of valuable information. Okay, variance and standard deviation. Really all they do is they measure how spread out the numbers are. Variance can get out of control. They have very large numbers, so the standard deviation, all it does is take the square root of the variance and it makes it more manageable. We can see here our sample variance and sample standard deviation. This is where the n comes into play. So we take the sum of the actual value minus the average, and then we square that, divide it by the sample size, n minus 1. The minus 1 is because of the sample. If it was the population variance, so all observations, then it would just be divided by n. For the standard deviation, you simply take the square root. So the very bottom picture shows several dogs, and the goal here is to measure their average height compared to the overall average. Once that's done, we want to see how much larger or smaller each dog is from the average, and we use standard deviation to tell us that. So we can see here we have the green line in the average, and then blue lines represent standard deviation. Very simplistic example of how variance and standard deviation is used. Next, correlation. I'm sure we all know it. We're just going to cover it here. It is a measure that indicates the extent to which 2 or more variables fluctuate together. If it's positive, it indicates the extent to which the variables increase or decrease in parallel with each other. A negative correlation indicates the extent to which one variable increases and the other variable decreases. And these values range from -1 to 1. The closer you get to the 0 value, the less significant the relationship is. So -1 and 1 represent perfect correlation. One moves in sync with the other. We move into high positive and high negative correlation. For the most part, the positive correlation, they both move together. The negative correlation, one moves one way, the other moves the other. For the most part, they move together. There are some odd occurrences, or maybe they don't do, one may not move them as much. And then again, the closer we get to 0, the more that relationship deteriorates. Simple linear regression. This is only comparing one independent variable to the dependent variable. It attempts to determine the strength of the relationship, and obviously dependent is denoted by y, and the other variables, the predictor, is the x variable. And here we're looking at body weight as the dependent and how height affects that. So we ran the analysis here, and we can see the data points on the screen are the dots and what's called the best fit line, the line where the squared difference from the data points to the line is the least. And it picks the best fit line is simply that. So this is the line that the least squares is the most efficient. In this case, the r squared is high. It's a 0.88. So there's a lot of predictive power here. Once the least squares line is plotted, which it is, it provides an equation an equation in the form of y equals a plus bx. In this case, weight equals 80, which is your intercept, plus 2 times the height in inches of the individual being measured. So fairly simple. Now I just want to highlight what SPSS software, a statistical software, third party, that you'll probably be using, what the output looks like and how to interpret it. So we have table 1 here, and that displays what variables are included in the method used to develop the model. So here we can see the variables included to predict the score in computer science course is the score in mathematics. And the method used was just enter, so it automatically puts it in. There are other ways of entering data, which is forward inclusion, which allows you to add variables until the model doesn't become any more statistically significant. And then there's also backwards exclusion, which includes all the variables and then pulls them out as the model becomes more significant, the lesser amount of variables that are in there. So that's what that tells you. Table 2 is the model summary table. For the model selected, it will display the validity of the model under the R-square. In this case, it is figure 0.3.299. And that's not overly predictive, but there is some merit to it. Table 3 contains the ANOVA, the analysis of variance. In this case, we want to focus on the F statistic and the significance. The F statistic, you want the value to be as high as possible, and the significance, you want a value of less than 0.05. So if your p-value to be statistically significant is 0.05, then you want that value to be less than 0.05. Which we can see, we have our F statistic at 14 and our significance at 0.001, so it is statistically significant. So we move forth with the model itself. Table 4 gives the user the model output. Obviously, the dependent variable is the score in computer science, and we tested to see if the score in mathematics was a predictor. And it was statistically significant, but it's mildly weak. And the model it gives us is in the form of, like we talked before, y equals a plus bx. So it's y equals our intercept, which is the constant, which is shown right here, 17.671 plus 4.55 times the score in the mathematics course. And that is the final model for the single linear regression. Now we'll just move into multivariate regression, which it's similar to what we just looked at, except we're looking at many different variables in it. It's a little more complex. There's a lot of steps that we're going to go through to make sure that we do it correctly and get the results that we're looking for. So we will go through those steps in the next slide here. We'll just run through the steps quickly. First off, we want to state the research hypothesis. Then we're going to state the null hypothesis, gather all our data, assess each variable separately first, look at the relationship between the independent variables one at a time to the dependent variable, assess the relationship between all independent variables with each other, calculate the equation itself from the data and the analysis, and calculate and examine appropriate measures of association and tests of statistical significance. That'll all be provided to us. Then we're going to make a judgment. Do we accept or reject the null? Do we accept or reject the research hypothesis? And then finally, we'll explain the practical implications of the findings and go from there. So, our situation. The DOT wants to understand the influence of various factors on the number of annual highway fatalities. Next, we're going to state the research hypothesis, which is what you think will happen. So, our research hypothesis is the number of fatalities is affected by the total population, the days that it snows, the number of days, and the average speed in miles per hour on the highways in the state of Wisconsin. Next, we'll state the null hypothesis, that there is no effect on using the variables that we provided that we think will be predicted, but there's just no relationship there. That is the null hypothesis. And that's stated simply, the number of annual fatalities is not affected by total population, days of snow, and average speed in miles per hour on Wisconsin highways. So, we gather the data. We have our dependent variable, and then for every occurrence of that, we have our independent variables. That step is done. When gathering the data, you must make sure that it's of high integrity. It's from a good source, you understand where it came from, and you're confident that it's correct. Always make sure that it's correct. Next, step 4 is we assess variables separately, and then we transform them if they're not normally distributed. Sometimes, or a lot of times in the financial markets, our predictors aren't going to be normally distributed. So, in order to satisfy one of the requirements for multivariate regression, it needs to be as close to normally distributed as possible. And in order to do that, we have a tool called the Tukey ladder of transformations, which transforms variables to meet the normal distribution expectation that the model requires. So if we have skewed data, like we have here, original data that is skewed, we can transform that using different powers. And we have these things here on the bottom in Tukey's ladder. You can do the log, you can do the square root, you can square it. Any way you can to transform the data to make it more normally distributed will enhance the quality of your model, and that is essential. Okay, step 5, compare independent variables to dependent variables. See how they look. Step 6, test independent variables amongst each other. What we're looking for is collinearity, which is double counting similar variables. And how we check for that is in the coefficients table in the SPSS output. So we're going to look at tolerance and the variance inflation factor, VIF. And in order for collinearity to occur, the tolerance has to be less than 0.2, or, I guess, or the variance inflation factor must be greater than 5. And we can see here on the table that these last two predictors have collinearity problems, and one of them has to be excluded, and then the model rerun to make sure that we encounter no more problems. So after that, we run the regression, and we can see here the final model is y equals the intercept 1.4 plus the the coefficient times the variable plus another coefficient times the next variable, and so on. And it's all coming from our table. So let's interpret the statistical output. Our R square is 0.78, which is, a very high degree of power there, so that's encouraging. And next, our statistical significance level is P has to be less than 0.05. We can see our three variables that turned out to be less than 0.05. The other ones were excluded, either for collinearity reasons or because they didn't meet the statistical significance criteria. Step number 9, do we accept or reject the null hypothesis? Well, we have a high R square with a statistically significant model. We are going to reject the null hypothesis, which leads us into step number 10. Do we accept or reject the research hypothesis? The research hypothesis is then accepted. Finally, step number 11 is interpreting the results. So the state of Wisconsin, which has a population of 6 million, on average 30 days of snow, and an average speed of 55 miles per hour, the estimated number of fatalities is calculated using the following formula. Y equals 1.4 plus 0.00029 times 6 million plus 2.4 times 30 days of snow plus 10.3 times 55 miles per hour gives us an estimated 2,379.9 fatalities annually in Wisconsin. That's pretty much multivariate regression in a nutshell, walking through the steps and interpreting the results. Okay, next we're going to explore logistic regression. And logistic regression, I'll refer to it as logit, is a type of probabilistic statistical classification model used for predicting outcomes of categorical dependent variables. Based on, you can have one predictor or you can have many. Again, this is, you can have univariate or multivariate. The process, is very similar to the regression model, except it returns a yes or no answer, or a zero or one, as you will experience. The following formula is used to determine what number will be classified as 0 or 1 by using betas or coefficients. And the larger number the model predicts in their alpha plus beta x, the closer it approaches 1. And the same, the smaller the alpha plus beta x, then it'll return 0. So we'll run through an example here. I'm not going to run through all the steps like we did in multivariate linear regression, because those can be carried over. This is just a brief overview of what logit regression is. So, situation. Did you evacuate your home to go someplace safer before Hurricane Sandy hit? And we have two outcomes. We can choose 1, yes, or 2, no. So we coded yes is 1 and no is 2. And the variables we included were, do you have pets? Yes or no. Do you live in a mobile home? Yes or no. How long have you lived in your current residence? And the education level that you have. So we ran the model and we got our results. We can see pets, mobile home, and tenure are significant. Right here in this column are significance. Another interesting output that SPSS states is that households with pets are 1.9 times more likely to evacuate than those without pets. And that's simply by taking 1 divided by your exponential beta. The other ones don't seem to be a huge factor here. So, in order to test the validity of the model, we can look at what's called a chi-square. And here, on the left-hand side, is what was actually observed, what the model observed. And on the right-hand side here is what the model predicted. So, the model predicted no evacuation correctly 93.18% of the time. That's very good. Although it predicted evacuation only 24.04% of the time. The overall model has a 69.53% accuracy. That's not bad. This is just a very simplistic example of how logit regression is typically used. When we develop financial models with it, we'll be using a lot more predictors involved, and it'll get more complex. This is just for basic understanding. And finally, data snooping. This got me several times. I want to make sure that I convey the message to you. It's dangerous. Data snooping is simply including information in models that technically hasn't occurred yet. It may be historical data, but before you make or you enter a position, you're pulling data from outside your scope. So data that if you were there live at that time, you wouldn't know what it is. For example, if your model calculates on a closing price, you can't enter on that closed price. You have to use the next open price, or you can't include an average true range of the next open in your model. That is considered data snooping. It'll make your model look really good. You'll get really excited, but nothing's perfect. Always double check it, and more than likely, if you have a fantastic model, you're data snooping. I just wanted to warn you of that. It happened to me numerous times. And if you're confused about data snooping, please ask more questions about it. And again, this concludes this module here. You can either ask myself or anyone else in the analytics department administering these modules. If you have any questions or help, we'll continue to work with these models as we go forth in future modules. So thank you for your time.